We're going to work towards writing Faraday's law as an equation, and the first thing we need to do is remember that we saw Faraday's effect. A current was generated when there was a change in magnetic field. That's what this PhET simulation shows. You can try this yourself if you wish. If I take the magnet and I push it into the coils, it makes the light bulb light up. So it's the change that makes a difference. If I just switch the directions of the field, then it makes it light up as well. Okay, so if it's the change that matters, we want to find a way to talk about the change in magnetic field. Let's throw back to when we talked about electric flux. Electric flux was a quantity representing the number of lines cutting through a surface. So electric flux was E dot A, or the integral of E dot dA. E was in newtons per coulomb, A was in meters squared. So our flux was newtons per coulomb times meters squared. It told us how many electric field lines cut through any surface. Now we're going to define magnetic flux, which is going to be the same sort of deal. Magnetic flux is a quantity that represents the number of electric field lines that cut through a surface. It's got the same sort of equation. It's the integral of B dot dA. Or if your magnetic field is constant and your area is simple, it's just B times A. So we use the integral for variable B and weird A, and we use B dot A for constant B. B is in Teslas, A is in meters squared, so the units of flux are Teslas times meters squared, or Webers, where a Weber is WB. So magnetic flux gets its own special unit. We can look at this in a picture. So if we have the magnetic field lines perpendicular to the loop or parallel to the area vector, and draw the area vector, stick straight out of the loop. So there's the A. So when the magnetic field is parallel to the area vector, so B parallel to A, you get the maximum flux. And this is just like electric flux. Okay, if they're not exactly perpendicular, then you have fewer lines cutting through. So in this case, the flux is equal to B times A times cosine theta. So fewer lines when you're at an angle. The area vector still comes straight out perpendicular. And then last, you have the fewest lines if your magnetic field lines are exactly perpendicular to the loop. In this case, the flux is B times A times cosine 90 equals 0. So when it's perpendicular, we don't get any lines cut through at all. Hopefully this is really familiar from when we talked about electric field lines because it follows the same sort of thing. Okay, let's do a flux example. We have a 10 centimeter loop. That implies that our loop is a circle. We know we're going to need to worry about area, and area equals pi r squared. That's going to be pi times 0.10 meters over 2 squared. So we know we're going to need to worry about area. The loop is in a magnetic field with a magnitude of 0.05 teslas. That's our magnetic field. Part A, what is the magnetic flux through the loop? So magnetic flux is equal to B dot A equals B times A times cosine of theta. Let's be careful about what we're going to put in here. B times pi r squared times cosine theta. So we know B, we know R. What about theta? So our magnetic field points to the right. I'll highlight one of those vectors. There's B. Our area vector is perpendicular out of the loop. So there's our area vector. Theta here is between B and A. It would be real tempting to put in 30 degrees here because 30 is on the picture, but the angle is not 30. The angle between B and A is actually 60 because the area vector is perpendicular to the loop. Okay, now we've got all the information to put in for our flux. So the flux is 0.05 teslas times pi times 5 centimeters squared times cosine 60 degrees to give us a magnetic flux of 1.96 times 10 to the minus 4 Teslas times meters squared or Webers. Okay, that's part A. Part B, what is the orientation of the loop to have maximum flux? Now this is just kind of a recap of what we did in the previous slide. To get maximum flux, your loop has to be upright. So this is maximum flux. This is where A is parallel to B. To have minimum flux, we don't want any lines to cut through that loop at all, so the loop is going to lie flat. So for minimum, A is perpendicular to B. So those are the relative orientations. There's parts B. What are the maximum and minimum flux? So part C, maximum flux has theta equals 0. So our phi maximum is equal to B times A times pi r squared times cosine 0. I'm not going to put in my numbers this time. That works out to be 3.93 times 10 to the minus 4 Webers. Minimum flux is when theta equals 90 degrees and magnetic flux equals BA pi r squared cosine 90 equals 0. Minimum flux when no lines cut through at all. Okay, then the next part, what is the flux if the loop rotates with an angular speed of 100 RPM? So we're going to take our loop, let's say it pivots around the center and it's rotating with an angular velocity omega. So our magnetic flux is equal to B times pi r squared times cosine theta. Theta is the angle between B and A. When it's rotating, theta is not constant. Theta is equal to, since it's an angular position, it's the angular velocity times time, where omega is given in radians per second. Okay, so our flux then, our magnetic flux, is B times pi r squared times cosine of omega t. Now all we have to do is a conversion. We've got omega as 100 RPM, where an RPM is revolution per minute. We want to convert to radians per second, so we remember there are 2 pi radians in a revolution, and there's 1 minute in 60 seconds. That gives us 10.5 radians per second. So our magnetic flux then is B times pi r squared. That's 3.93 times 10 to the minus 4 Webers times cosine. We can't put in a number here because the flux depends on what time it is, but it's going to be times cosine 10.5 radians per second times t. So there's your magnetic flux if it's rotating. We see that it changes.